Good afternoon and welcome to the 30th of our NASA Engineering and Safety Center Guidance, Navigation and Control webcasts. I am Neil Dennehy, the NASA Tech Fellow for Guidance, Navigation and Control, and I'll be moderating today's webcast. The idea to have these hour-long webcasts originated several years ago with the members of the NESC GNNC technical discipline team, who thought this would be a good way to broadly share their individual knowledge with the rest of the NASA GNC community of practice. Please note that this webcast is being recorded and will be made available for subsequent viewing on the NESC Academy site by visiting the same URL as today's event. I'm now very pleased to introduce today's speaker, Professor Peter Seiler from the University of Michigan. From 2004 to 2008, Peter worked at the Honeywell Research Labs on various aerospace and automotive applications, including the redundancy management system for the Boeing 787, sensor fusion algorithms for automotive active safety systems, and reentry flight control laws for NASA's Orion vehicle. Previously at the University of Minnesota, Peter worked on advanced control techniques, fault detection methods for safety critical systems, and robust control of disk drives. Peter's research is grounded in robust control theory, which focuses on the impact of model uncertainty on system design. Peter's full biography is on the webcast registration site. Peter's talk today is entitled Robust Stability, from Disk Margins to Neural Network Analysis. In his talk today, Peter will give us a tutorial introduction to disk margins. These are robust stability measures that account for simultaneous gain and phase perturbations in a feedback system. This provides a generalization of classic gain-only and phase-only stability margins. The talk will motivate the use of disk margins and provide several examples, including applications to multiple input, multiple output control systems. The talk will conclude with some recent extensions of this basic robustness analysis framework. At the end of the talk today, I will moderate a 10-minute question and answer period. You can submit questions to Peter via the Ask a Question button toward the bottom right of the webcast player. Please include your email address, simply your name and center location when you're submitting your questions. Because of the 10-minute time constraint for the Q&A period, Peter will most likely only be able to directly answer a few of the questions that he receives from the audience today. As long as we have your email address, Peter will respond to all the questions that he receives. I encourage you to submit your questions as they arise during the course of the talk, rather than waiting to the very end of this webcast to submit your questions. If you have issues viewing the webcast, we recommend that you refresh your browser. And now, I'd like to turn this webcast over to Peter.
Great, thank you for the introduction, and I appreciate the chance to come and give a talk today. As Neil said, this will be a talk about disk margins, and it'll mostly be tutorial. So, I'll start with kind of classic gain and phase margins and talk about why we want to extend disk margins. So, jumping in. So here's kind of the outline for the talk. I'll talk about disk margins, what's the motivation, talk a little bit about disk margins for SISO systems, and then I'll talk about multi-loop margins. And then with the time left over, I'll talk, as like Neil mentioned, about some extensions to things like linear time-varying systems along trajectories, and also neural network-based controllers. And Neil mentioned it would be nice to give some additional reading. So if you find any of these topics interesting, the top half gives kind of reading material for disk margins. There's a tutorial paper that I wrote with my former late colleague, Andy Packard, and Pascal Gahi. And there's also a really nice 7-minute summary video by Brian Douglas, and then some kind of MATLAB documentation functions if you're interested in kind of doing something computational. And then the last half of the talk, I've given kind of 2 reference papers, and you can kind of follow the references from there. All right, so moving into the first part. So just kind of to set the stage, the classical margin problem looks like the following. We've got a plant K and a controller, or plant P and a controller K at the bottom. And we assume that we've designed the controller so that's stable. And then we introduce a perturbation between the plant and the controller. And this perturbation F is meant to model dynamic variations in the plant. So we've got a plant model that we're using for the control design, and we'd like to make sure that the controller still stabilizes the actual model. And the type of variations that we capture in sort of the classical margin problem are either like real gain variations. So we set F to be some real number G, And we ask the question, how far can we perturb the gain away from the nominal value of 1 before instability occurs? That's how we would define a gain margin. And there could be an upper gain margin and a lower gain margin. And then the phase margin problem is we allow f to just be a pure phase, a complex number with unit magnitude. And we ask how much the phase can vary away from 0 before instability occurs. And that models things like phase variations in the plants or time delays due to computational processing and so on. So that's the classical setup. Now, why might you want to move beyond that? So this is maybe just one example. This is on the right is a collection of disk drive experimental frequency responses. Those are the blue curves. And the gold curve is a low order model. So the behavior of these disk drives, which is basically just a rotating beam, if you want to think about that. The disk drive basically has a voice coil motor at a hinge, and then that rotates or moves the head so that you can read and write data. Now, at low frequencies, the model is basically a double integrator. This is like a rigid body Newton's law type model. And as you go to higher frequencies, then you get flexible modes appearing. So even though the arm is made out of metal, it's at high enough frequencies, it's got some flexibility to it. And you can model, you can create a low order model, design a controller for that. That would be the gold. But at really high frequencies, each part is just different in terms of what the flexible modes are and what the frequencies are. And so this is an example that's kind of common across many electromechanical systems. Launch vehicles have slosh modes and flex modes. Aircraft have flex modes and so on. So we want to be able to design a controller with a low order model, but then be robust to these variations. So what are some of the limitations of classical margins? Well, first off is that real systems differ from their mathematical models in both magnitude and phase. So the classical margin problem is either a gain variation or a phase variation, but not both. But this sort of data indicates that there's really a lot of variation in both gain and phase. The second reason is that you can have problems where you can have really large gain and phase margins, but they can be not very robust. And so the picture that's shown on the bottom is, it's a bit contrived, but it highlights the issue. It's a Nyquist plot. In the Nyquist plot, if it touches the -1 point, that's going to be unstable, assuming it's got the right number of encirclements. This example is one where the loop is stable. The gain margins are actually rather big because the loop doesn't really cross the it doesn't cross the real axis except for at the green dot. And the phase margins are large because it only crosses the unit circle where the other green square is. So this has good gain and phase margins, but it's very close to coming to the -1 point. And so if you are doing some sort of optimal control-based design, occasionally, if you don't account for this sort of, if you only account for classical margins, you can kind of get into these kind of weird paradoxes where you've got really good gain and or phase margins, but the combination of the two could cause you to be unstable. The third part is that margins have to account for the increase in model uncertainty at high frequencies. So typically when we talk about things like linear quadratic regulator, we say it has infinite gain margin and 60 degrees of phase margin. And that's good as long as the bandwidth is not too high. So what the picture is showing on the bottom is if the bandwidth is not too high, the gold model is a relatively accurate representation of the blue experimental data. 45 degrees of phase margin and or 60 of gain margin may be a reasonable rule of thumb. If you go to high enough frequencies, though, all bets are off. The model is not an accurate representation of the data. And this is true for most electromechanical systems. So usually when people talk about rules of thumb, there's usually a 6 dB, 45 degrees of phase margin rule of thumb. That's with an implicit assumption that you haven't pushed the bandwidth out so far that your model is completely inaccurate. So you need to account for that as well when you're talking about margins. And then the last sort of limitation or the reason to maybe move beyond classical margins is the extension to MIMO systems. And I'll talk about that in the second half of the talk, which is there are more natural robustness margins that extend to MIMO systems in a more natural way as opposed to classical margins. So that's the motivation. So now let me define for you what I mean by these disk margins. So the setup is going to be the same. It'll be a classical, I'll do this in the SISO case to begin with. It'll be a SISO loop in the upper right-hand corner. We're going to inject a perturbation F, but this perturbation now is going to allow for gain and phase variations. So if you focus on the picture on the bottom right, that's a picture in the complex plane. The horizontal axis is the real axis, and the vertical axis is the imaginary axis. And where the red cross is, that's F equal to 1. So that would be the nominal value. You'd say I designed the feedback system so that when F is equal to 1, this is stable. And I want to know how much can I perturb the gain away from 1 and remain having a stable feedback loop. And the distinction now is in gain margin analysis, you would only perturb F along the horizontal axis. You'd only use real sort of gain variations. And in the phase variation problem or the phase margin problem, you'd only perturb F along things that have pure phase. And in our setting, we're going to allow F to perturb to allow both gain and phase. And we're going to want to know how big can I make a disk around F and remain stable. Now, there's lots of ways of defining disks that are complex gain and phase combinations. The most common way that's used in the literature is something called a symmetric disk. And that's defined algebraically in the upper left-hand corner. So it looks like 1 plus delta over 2 divided by 1 minus delta over 2. Now this weird, I guess it's maybe not the first thing you might think of doing. This disk is symmetric. Well, first off, it's a disk of gain and phase variations around F equal to 1. Because if you plug in delta equal to 0, you get a perturbation just of 1. That's the nominal value. As delta moves away from 0, though, you get a gain and or phase combination. So the disk grows. There's an alpha parameter that defines the size of the disk. The disk grows as you increase alpha. So just kind of graphically, the bottom kind of depicts that. Small values of alpha are kind of small disks. And then as alpha grows, you get bigger disks until it eventually covers the whole right half plane and then even bends over into the left half plane. So we're going to think of the level of alpha as going to be the size of the disk. The other thing is that the disk is symmetric in the following sense. The way I've defined the disk above is it passes through two values on the real axis, gamma min and gamma max. And it's symmetric in the sense that gamma min is the inverse of gamma max. So to put some kind of concrete numbers here, if gamma min is 1/2, then gamma max is 2. So those two numbers are geometrically, they're the same factor above and below 1. Or if you prefer to think in dB, this would be a disk of plus minus 6 dB. That's the sense that it's symmetric. It's symmetric in units of dB, about the nominal gain of 1. So that's the disk that we're talking about. We're going to talk about margins using this disk. I'll come back to this later, but this disk will also be able to tell us something that we can connect back to gain and or phase variations. So if I tell you there's a certain disk margin, and I'll quantify it in terms of this number alpha, I'll then also be able to tell you that you're stable for all gain variations between gamma min and gamma max. And I'll also be able to tell you that you're stable for all phase only variations up to a size phi max. That's the phi max listed in the paper or in the diagram here. So if you prefer to think in those numbers, I'll be able to kind of relate these disk margins back to the classical margins, just keeping in mind that the disk margin actually tells you something more because it's allowing both gain and phase variations simultaneously. Now, what's the definition of the disk margin? The definition of the disk margin is what's the largest value of alpha for which the closed loop is stable for all the perturbations in the disk that's defined by d of alpha. So remember, alpha is the size of this symmetric disk. And I want to tell you what's the largest disk for which I can prove stability. So that'll be our definition. I'm going to give you a condition for how to compute this disk margin. So I need to tell you kind of two pieces of notation. The first is the notion of the sensitivity transfer function. So that's the transfer function from the reference to error. And I've written nominal here because that's the sensitivity without just setting this perturbation f equal to 1. Okay, so that'll show up in the condition that I'm going to tell you. And the second thing I need to tell you is the notation for the H infinity norm. All this is the peak on the Bode plot. So if I plot the Bode plot of the sensitivity function, and I look at the peak across all frequencies, including infinite frequency, that's what I'm going to call the H infinity norm. So just peak on a Bode plot, but that notation will appear in the next slide. So now here's the result. If you give me a feedback loop, a plant P and a controller K, and it's nominally stable, meaning it's stable, plug in F equal to 1. I can tell you that you're going to be stable for all perturbations in the size of the disk alpha max, where alpha max is given by 1 over the infinity norm of S minus 0.5. Now this S minus 0.5 maybe seems a little odd, so let me try to justify where this comes from. The basic proof is something like the following. The characteristic equation is how you figure out where the poles are. So now the proof goes something like this. There's a perturbation F that puts the pole on the imaginary axis at some frequency, let's say j omega naught, if and only if the characteristic equation has a root there. So the characteristic equation is 1 plus F times the root evaluated at j omega naught. Now, if you plug in that F has this form that depends on delta, and you solve for delta, then you get that delta is equal to 1 over S minus a half. So the point is that a perturbation will put a pole on the imaginary axis if and only if delta has this expression in terms of S. Now you could ask the question, well, what's the smallest delta or the smallest disk that'll put a pole on the imaginary axis? Well, you get that by maximizing the denominator, or in other words, finding the frequency where S minus a half is as big as possible. So that's kind of roughly what the idea is. So if you want to find the smallest disk that causes instability, you try to make the sensitivity minus a half be as big as possible. And the frequency where that occurs is the frequency where you get the smallest disk margin. So you could basically, this is another number that you could just pick off a Bode plot. You'd have to plot a Bode plot of S minus half, figure out what the peak frequency is, and then take the inverse of that peak magnitude, and that would give you the largest disk. And there's a little bit more to it than that, in the sense that you can also then construct a perturbation that will cause an instability. So that's kind of the next comment here, which is not only out of this calculation, not only do you get a disk margin, which is a disk that says you're stable for all gain and phase variations inside this symmetric disk, but you might ask, well, this is a little bit unusual because I'm going to destabilize the system with a complex number. And I kind of skimmed over the proof, but there's a way of constructing what the complex number is that will cause you to go unstable. Well, it turns out that that complex number can be interpreted as a state space system, meaning if you give me a complex perturbation F naught, you tell me the frequency where it causes the instability, I can then construct a state space system with all real coefficients that will also destabilize the system and will stay inside the same disk. And the reason why this is useful is then you can go drop that perturbation into like a higher fidelity simulation. You've got maybe a nonlinear simulation that's high fidelity, and you've done this disk margin analysis on a linearized model. Well, now I can take this perturbation, plug it back into the simulation, and verify whether or not it's a problem in some higher fidelity setting. So I think that's a useful thing. So let me give you an example just to make this a little more concrete and show you just at the code level how this would play out. So this isn't meant to be any sort of physical system, but there's a plant with a proportional controller, gain of 25. So the loop is just the product of P and K. And the Bode plot is given at the bottom. Okay, so in the magnitude in dB and the phase in degrees. Both plotted as a function of frequency in radians per second. So the classical margins you would compute by figuring out where there's a gain crossover frequency or a phase crossover frequency, and you'd figure out what those gain and phase margins are. So the classical margins here are a gain of 3.6, the frequency is 3.16 radians per second, 29 degrees of phase margin at 1.78 radians per second. So the gain margin occurs where you compute that at the frequency where there's 180 degree phase crossover. And the phase margin you compute at the frequency where there's a gain crossover frequency. Now this disk margin you compute by plotting the Bode plot of S minus half, figure out where the peak is. It turns out that occurs at a frequency of 1.96. You take the inverse of that gain, and that gives you a alpha corresponding to the disk margin of 0.45. I said it's useful to then convert that number into something maybe you're more familiar with, which is the classical margins. So this symmetric disk margin implies that the gain margins are at least 0.63 to 1.59, and the phase margin is at least 25.8. And you'll notice that these margins, these kind of equivalent gain and phase margins that you're getting from the symmetric disk margin calculation are less than the classical disk margins. And that's because they're implying that not only do they imply those levels of gain and phase margins, they also allow you to kind of vary the gain and phase simultaneously. I put just a little bit of code here just as like sample reference. If people want to look through this later. The left side shows how I computed the classical margins. Just in MATLAB, there's an all margin function that'll compute the classical margins. The right side is how you compute the disk margins. And I've done it two ways on the right side. The first way is I just compute the norm of s minus a half, and take the inverse, and that's how you figure out what the disk margin is. The second part is there's a built-in function in MATLAB that would just do that. This is the disk margin function, and that returns more information. It returns what's the equivalent classical gain and phase margins. It returns the disk margin. The upper and lower bounds I'll talk to briefly later. They're not relevant here. They're just equivalent to the disk margin itself. And then the last thing I'll point out is the box at the bottom, which shows that it also returns a state space model with a perturbation that remains, close to a gain of 1, but within inside the disk that's given by the disk margin. And it also destabilizes the system. So if you took that state space model and dropped it between the plant and the controller, formed the closed loop, you'd find that there'd be a pole on the imaginary axis at the frequency 1.95 radians per second, which is the frequency where this disk margin analysis indicates that there's a problem. Now, one other nice thing about these disk margins is that they give you some frequency-dependent information. Typically, when you do gain and phase margin analysis, you only get numbers at the phase or gain crossover frequencies. With these disk margins, you can actually cause an instability because they're complex. At any frequency, you can put a pole on the imaginary axis of a certain size. So then what you could ask is, at each frequency, what's the smallest disk for which there is an instability at this particular frequency? So what this plot is showing, the top shows the loop just for, it's a made-up example. It's not a physical example. The bottom left shows the Bode diagram for this loop. Magnitude and phase is a function of frequency. And the right two subplots are the disk margins as a function of frequency, but interpreted as their equivalent gain and phase margins. And so this disk margin concept allows you at every frequency to tell you how much gain and phase can you tolerate at this frequency before you go unstable. Now this is useful because you'll notice on the left there's a resonant mode around 10 radians per second in the loop. And on the right, you're seeing there's a sharp drop off in the disk margin, interpreted in terms as gain and phase margins. You're seeing those numbers drop down at 10 radians per second, saying I'm able to tolerate less gain and phase variations at that frequency. And you're also noticing low gain and phase kind of margins at around just under 1 radian per second. So these plots then give you like a whole spectrum. Like you can look at how robust you are as a function of frequency. And typically with electromechanical systems, you can then relate that back to what's happening in your physical system. It could be related to there's an instability caused by a slosh mode in a launch vehicle or a flex mode in a commercial aircraft. And so these plots, I think, just give you a little bit more insight into, why, if there is a stability margin problem, what sort of frequency is causing it and why. Now, the next or kind of last part that I want to talk about with disk margins is the extension to the multi-loop or the MIMO case. So let me first kind of motivate it with what's called loop at a time margin. And I'll just talk to a 2-input, 2-output system. So the loop at a time margins are computed like the following. I've got a 2-input, 2-output plant. I've got a 2-input, 2-output controller. And typically in this analysis, you would say, insert the perturbation in one of the loops and leave the other loop closed. And you want to ask the question, how stable am I going to be, or how much can I change the gain F1 away from its nominal value of 1 by either injecting a gain or a phase. So you're basically going to do gain or phase type analysis with only one loop. So that would go kind of the following way. You close the second loop. You can then take the diagram on the top and you can redraw it as an equivalent SISO problem. where the L1 in the bottom picture depends on the plant of the controller in the top picture, and you close the second loop. Then you ask, well, how much gain or phase variation can I inject there and go unstable? That's the SISO problem, and it tells me how robust I am to perturbations in the first loop in the diagram on the top. And then I could do the same analysis in the second loop. And those would be loop at a time margins at the plant input. And I could do the same analysis at the plant output. And in MIMO systems, those margins at the plant output can be different than the margins at the plant input. In the SISO case, we typically don't worry about that because the margins at the plant input are the same as the margins at the plant output if there's only kind of one input, one output. And the problem with this sort of analysis is it doesn't account for cross-coupling. The loops themselves can interact, and so this can be overly optimistic. So by that, I mean, I could have very good margins if I only inject a perturbation in the first channel. I could have very good margins if I only inject perturbations in the second channel. If I inject perturbations in both the channels, it's possible that some small combination of the two can go unstable. And so kind of the multi-loop disk margins are an attempt to sort of account for that cross-coupling. So the multi-loop disk margin analysis looks like the following. If you, again, focus on the 2 input, 2 output case at the bottom of the slide, you can inject perturbations in both the plant input channels. And then I put kind of in the first bullet, I said you could also do it at the output if you wanted to. Or you could inject 4 perturbations, the F1 and F2 that are shown below, and then you could inject an F3 and F4 at the plant output. But let me focus on the plant input just to make the discussion concrete. These 2 perturbations now are allowed to vary independently. The F1 is not necessarily have to be equal to F2, but we're going to say they both live in the same disk, and we're going to use this kind of symmetric disk that I defined earlier. And we're going to ask how big can we increase that disk and still maintain stability for all complex gain and phase perturbations in the disk. So F1 and F2 will move around in this disk in a gain and phase. F1 will be independent of F2. And we'll just ask how much kind of variation we can tolerate in these 2 channels. And this margin, the computation of it, when I did the SISO case, I gave you an explicit formula that involved the sensitivity function. As you inject kind of more perturbations, the computational theory is, there's kind of a more general computational theory to do this calculation. So that's known as the structured singular value, or mu. So I won't talk too much about how the calculations are done, but there's a little more details involved in that. So let me give an example that just kind of, this is maybe an academic example taken from an old paper by Doyle that kind of highlights what can go wrong. So here's a 2 input, 2 output plant. The constant A that's given there is set equal to 10. So it's got a resonance. If you look at the plant, it's got 2 states with a resonance at J times 10 radians per second. And then the feedback controller is just a unity feedback. And if you do the classical loop at a time margins, the first loop says the margins are great. The gain margins are 0 to infinity, and you've got 90 degrees of phase margin. The second loop is also great, infinite gain margin and 90 degrees of phase margin. So it looks like everything is great if you do the loop at a time margins. If you do the multi-loop margins at the input, that disk is very small. And if you do it at the input and output, it's even smaller. These kind of values I've listed for alpha max are small values. And to put this into context, you can actually destabilize the system by changing the gain of the first loop down to 0.9 and changing the loop of the second, or it's changing the gain of the second loop up to 1.1. So a very small combination of perturbations in the 2 channels interacts kind of in such a way that you can destabilize the system. And so this is sort of an example that highlights why just looking at one loop at a time, if you hold the second loop at its nominal value, you can vary the first loop by a lot. And the same thing for the, vice versa for the second loop. But it's really the combinations of the 2 loops that can cause problems. And I mentioned early in the talk that there was a nice YouTube video by Brian Douglas on disk margins. And he gives kind of more motivation on how this type of issue appears in kind of physical systems. And the type of systems where this appears is typically where you've got cross-coupling and you try to do a controller that tries to invert out plant dynamics. And in MIMO systems, that can make you extremely sensitive to the plant model. And this multi-loop disk margin is maybe the first kind of extension, I would say, of classical margins that highlights this sort of issue with MIMO systems. In terms of computational tools, you can do all this also in sort of like a Simulink type environment. So this picture is just meant to show like a little demo of an airframe model. So the upper left is a little longitudinal aircraft model with pitch rate Q, acceleration AZ, and the red dot is like there's a syntax in Simulink where you can say, I want to introduce a little bit of disk margin uncertainty at the point of the red dot. And then if you click down into what's called the airframe model in the upper left-hand diagram, in this Simulink demo, there's another diagram, which is the one in the lower right. And I could inject two other red dots saying, well, I want to worry about uncertainty where those red dots are. And those correspond to uncertainty in how the vertical force is generated, the aerodynamic vertical force in this aircraft, and how the aerodynamic moment is generated. So I can go into a Simulink diagram and there's kind of a click sort of syntax, or there's a command line syntax that says, hey, there's 3 spots in this diagram where I think there might be uncertainty. So the motivation of this diagram might be, I have uncertainty in how the aerodynamic forces and moments are generated. And I also have uncertainty in how the actuator is modeled at the fin deflection for this aircraft. And I would like to understand how variations in all 3 of these channels simultaneously, how am I robust to that? And that would be a kind of a more generalized notion of a multi-loop disk margin problem, and all that at the command line is just a few lines of code. Kind of moving beyond kind of classical SISO gain phase margins, I've talked a little bit about the MIMO case with multiple uncertainties, and just to give you maybe more like reading material or things to think about, if you think about even more general case, there are 2 kind of more general frameworks. I've alluded to the structured singular value, which is really a framework to think about non-parametric or dynamic model uncertainty. Think of that as like a tube in a Bode domain. I've got a nominal model, and I put a tube of possible, unmodeled dynamic variations. Or it can handle parametric variations, things like mass uncertainties and so on. Then even more general than that, there's a framework called integral quadratic constraints. It also handles things like actuator saturation and rate limits. And both these 2 frameworks, they have a long history. They go back to things like the absolute stability problem back in the 40s. People were trying to understand what's the impact of a nonlinearity like saturation. And then there was kind of I'd say a key revival in the 80s and 90s. A lot of it was related to the shuttle work. And so I've listed some of the kind of key contributors to both the structured singular value and the IQC type framework. And then the third bullet point that I've listed here is I've focused just on stability margins. But these tools kind of generalize if you're interested in things like how big can the gain get, meaning the loop remains stable, but how bad can performance get? So those would be questions about robust performance. And so there are kind of extensions from just talking about stability to what we would call robust performance analysis. Okay, so I have maybe a little over 10 minutes left. So I just want to spend a little bit of time talking now about some maybe non-standard or non-classical controllers. So the first part of the talk, these disk margins are really for the case where the plant and the controller are both linear time invariants. So let's say that's the kind of standard setting. And the last part I want to focus on are things where there could be time varying or not neural network type controllers. And let me just briefly try to motivate this. So the first is just thinking about time varying systems. And I think the extension here would be things like, let me focus on like, let's say rocket launchers. You're going to launch a vehicle, it's going to follow a trajectory, and in some certain, let's say t seconds, it'll be where it's supposed to be in outer space or at the end of some stage. So you're going to have a trajectory, you're going to linearize along that trajectory, and you're going to get a time varying linearization. And it's going to be finite horizon. The trajectory is going to end at some time. It won't go on forever. So in this setting, to talk about linear time invariant systems or infinite horizon stability, those were implicit assumptions of the formulation when I talk about disk margins. They don't hold in these finite horizon time varying kind of linearized trajectory type problems. So it'd be nice to think about what does it mean to talk about margins in those sort of settings. The other thing that's maybe non-classical is to have just different controller architectures. So I've listed kind of 3 here that I think are kind of compelling things that people are working on. The upper left is like a picture just with a plant and a neural network controller. The right-hand side one is just thinking about adaptive controllers. And I've listed some of the kind of more recent work that's ongoing at NASA. And then the lower left is just optimization-based control. You're going to land let's say a lunar vehicle, and you're going to use just optimization in real time, something like model predictive control or some other type of optimization. In all 3 of these settings, I think there's a need to think about what does it mean to be robust to model variations. You're going to design these controllers using some model, but you're going to implement it maybe on a system that has a different model. And what does it mean to talk about robustness in these settings? And so for the rest of the talk, I'm going to focus just on the neural network case, because that's kind of where we have some preliminary results. And I think the other 2 cases are interesting, and it would be nice to think more about them. So I've given kind of 2 details. I won't talk about the time-varying systems. If you're interested, I've given kind of a paper reference. But basically, the idea is you linearize a long trajectory, and then you have to think about robustness margins for linear time-varying systems. And so we've got some results there. But I'll focus on the case of neural networks and just try to highlight how this plays out and try to tie it back to the disk margin case. So here's the setup. I'm going to do the simplest case where G is linear time invariant. And the neural network, the pi that's listed here, is just a static state feedback. So you measure the state X, and then the neural network spits out a U. And the neural network could be trained by reinforcement learning or some other method. Now, the neural network has the following structure. You take the state X, let's say that's the input, I'll call that W0. And then each of these W, the lowercase w with superscript i's, are going to be like variables for each of the layers. So the neural network maybe has L layers. And each layer corresponds to take the variable w from the previous layer, multiply by capital W, which is a set of weights, add a vector b, which are the biases, and then run it through a nonlinear function, which is called the activation function, and just keep doing that repeatedly. So the neural network is just composed of linear operations, multiplication by capital W, adding a bias b, and then applying an activation function. And so we want to be able to assess or think about robustness in this setting. So the first point that we're going to think about is just, can I even prove stability for something like this? And if I can I prove a region of attraction? Meaning, let's presume we're going to talk about local stability. What's a set of initial conditions for which I can prove that will converge back to an equilibrium point? So the basic approach looks like the following. We take the neural network, and I already gave you or told you that it has some special structure. It's got weights and biases, which are linear operations, and then it's got a bunch of nonlinear activation functions. So the first thing we do is we separate the easy part, which is the linear weights and bias operations, from the nonlinear activation function part. So without going into detail, we take the picture of the pi and we split it out into this picture in the lower left-hand corner. The n here just has all the weights and biases embedded in it, and the phi has all the nonlinear activation functions all stacked up together. So that's the first part. Then the second part is to write local constraints on the activation functions. So the activation function looks something like a hyperbolic tangent. And the hyperbolic tangent, we're going to be doing this about some equilibrium point. That's the little x here. And basically, we're just going to write quadratic constraints around that point. So the red sector here, those lines are basically 2 slopes, saying that the hyperbolic tangent, it lies between those 2 slopes. And we can express that as quadratic constraints. But roughly, the approach, what we're saying is the nonlinearity is hard to deal with, but I can bound it between 2 linear functions. And that bounding property is something that I can then do some analysis on. The global sector is basically saying that the hyperbolic tangent lies between the 2 red lines for all values of the input. Now, you can write local sectors as well, and those would be kind of the tighter green sectors. They're kind of smaller sectors that only hold over a smaller interval of the input. So that, if we get down to the nuts and bolts of it, that's makes the analysis less conservative. Now, the last part, without going into too much detail, these local quadratic constraints, You can combine that with Lyapunov theory and some convex optimization to estimate the regions of attraction. And I'll show you some examples. But that's kind of at the core of it. The local quadratic constraints are one way of like putting some linear bounds on the nonlinear activation functions. And the approach that we're taking, I mentioned kind of a lot of this theory dates back to the 40s and 50s. It's really not much different than the theory that's used or was used in the 40s and 50s to think about the impact of a saturation in the nonlinear, or what's the impact of saturation on a feedback system. It's just now the nonlinearity is arising as part of the neural network rather than as part of an actuator model. There's a couple comments at the bottom. I try to roughly explain the case where the plant was linear time invariant. We can extend this to handle the case where the plant itself has, a subset or certain classes of nonlinearities or uncertainties. And we can even think about disk margins in the way that I already described, coupled with plants that have neural network-based controllers or feedback systems with neural network-based controllers. So you could ask the question of, I've designed a neural network. Is it stable? If it is, how much disk margin uncertainty can it tolerate? And that would be a useful way of tying back sort of classical margins to a neural network type controller. So let me just kind of briefly give a few examples before I conclude. So here's a little simple academic example. It's an inverted pendulum. I've given it in continuous time. The paper that I reference is actually all in discrete time. So the dynamics were discretized. The plant has some trigonometric terms, sine of theta. So theta here is the angle and theta dot is the rate of this inverted pendulum. So we can bound those with sector constraints as well and handle the nonlinearities in the plant. We trained the neural network through reinforcement learning. It's not a particularly big neural network by kind of today's standards, but it has 2 layers, 32 neurons per layer, and we use the hyperbolic tangent as the activation function. And in this case, we set all the biases to 0, just so that the equilibrium point would be at theta equal to 0. And so the results look something like this. This is a plot of a provable region of attraction. The horizontal axis is the angle. The vertical axis is theta dot. The gray lines are just simulation trajectories. So it's a 2-state system, so you can just plot the phase plane. And the blue curve, or the blue ellipse, is the region that our method says every initial condition inside this blue ellipse will converge back to the equilibrium point. The equilibrium point being that black cross at the center where theta is equal to 0 and theta dot is equal to 0. The other orange lines kind of that are canted at a kind of going crossways, and the vertical lines are basically local regions that we have to make some a priori assumptions in order to kind of build these local quadratic constraints. So I didn't kind of go into too much detail about that. But the paper has more details. As sort of maybe another example, this is a model of a 4-state lateral vehicle control. So imagine you want to do autonomous driving. You want to stay close to a center line. The model here has 4 states. There's a distance from the center of the vehicle to the lane edge, that's E. And then you have the angle between the longitudinal axis of the car and the lane, that's E theta. And then you have their 2 rates, E dot and E theta dot. So the model is given here, the parameters are given in the paper. I'll kind of skip over the details. But we might want to ask the question, will our controller keep us on the center lane? So in this case, we again design a neural network using reinforcement learning, 2 layers, 32 neurons per layer. And we also include some dynamic uncertainty in the model for the car, and then we include actuator saturation. And okay, those are details about the neural network. And again, we get provable regions of attraction. So the left and right are subplots showing the slices of the region of attraction. The left subplot shows the lateral error with respect to the lane edge and the rate of that error in the vertical axis. And the right subplot shows the angle between the longitudinal axis of the car and the lane. And then the vertical axis is the rate of that variable. So these are 2 slices in a 4-dimensional plane. The initial conditions inside the blue ellipsoid converge back to the equilibrium point, which is 0 lateral error and kind of perfect heading. All right, so I think the time's kind of coming close to a close, so let me kind of conclude. The first part of the talk is really just kind of this tutorial on disk margins, and trying to motivate them as natural extensions to classical margins. I talked a little bit about, I guess the main point is that these allow for simultaneous gain and phase variations, and they have natural extensions to multi-loop margins. And then more generally, there's kind of this structured singular value integral quadratic constraint framework that kind of is an overarching framework to kind of capture all these problems. And then the second part of the talk, in the last kind of 15 minutes, I just talked about some kind of more recent kind of academic work, trying to think about what is it, how can we assess stability and robustness of non-classical controllers? And I talked about 3 types of problems, but I really focused on the neural network-based controllers. And then I think as future work, I mentioned kind of 2 other classes of controllers, adaptive and optimization-based. And I think we have tools, in both these settings, but they're just not as well developed as they are in the linear time invariant case. So I think having additional tools to think about the robustness in those settings would be useful, and that's kind of ongoing research. I think with that, that's the last slide, and I'm happy to take some questions.
Well, thank you very much, Peter. I appreciate, I think the community appreciates you taking the time today to share some of your knowledge and insights on robust stability for control systems. Very, very provocative, some of what you briefed. Yeah, it's been an interesting presentation, and it has generated several questions. Let me start off with the following question. Is there something equivalent for the alpha parameter that you talked to us about that, in disk margin that matches or comes close to the classical gain and phase margin rules of thumb? Is there a rule of thumb for alpha that's analogous to 6 dB and 30 degrees that we know from classical control theory? Does that make sense, the question?
Yeah, that's a great question. So here's the slide where I showed the disk. So I said if gamma max is 2, then gamma min would be 1/2, and that would be roughly corresponding to plus minus 6 dB. My recollection is that corresponds to alpha equal to 1/2. And I would say a number slightly less, I'm sorry, I said alpha equal 1/3. 1/3 was the number I meant to say. So alpha equal to 1/3 would correspond to gain margin of plus minus 6 dB. Now it's actually more than that because you're allowing both gain and phase variations. So a number slightly less than 1/3 would roughly correspond to plus minus 6 dB, which I think is the standard rule of thumb.
Mm-hmm. Great. Let's see. This is a little bit of a curveball, but we're here to challenge you today. One of the viewers, I think you referred to a YouTube video that covers some of this. I think that was one of your references up front. And someone went and looked at that YouTube video. And there was an example in there that had a diagram that showed a rather large area of stability. And then the disk only covers a small portion of that. So this person who watched the YouTube video wanted to know, is it possible to generalize that to maybe like an ellipse margin instead of a disk to take the disk? I think that stems from what we saw here today was the disk margin reports some conservative margins relative to the classical way of doing it. But again, it's simultaneous gain and phase margins. We get that. Anyhow, yeah. Any thought about a different shaped disk, like an ellipse?
Also a great question. Okay, I'll answer it in a slightly different way, which is not thinking about ellipse. But I mentioned there's lots of ways of defining the disk. And here I use what's called the symmetric disk. There's also disks that you can define that are kind of more skewed to the right in this diagram to the lower, kind of in the lower part of the slide, or they're skewed to the left. And skewing that disk to the right or the left actually can prove kind of bigger regions. And the documentation on MATLAB, I think they've got some examples where they talk about this skew and how you can get different disks that give you different conclusions about what the margins are. As a starting point, the symmetric disk is what most people would use. But if it ends up being too conservative in a particular example, it may turn out to be that a skewed disk one way or another gives a less conservative answer. I'm not sure about ellipses.
Okay. But that's an alternative of something different than a symmetric disk that you were just describing.
Yeah, the paper reference that I gave talks a little bit more about that kind of skewing and how it can give different answers.
Mm-hmm. Good. Thank you. This is a little more of a philosophical question, but one viewer has asked, why did it take the community, the GNC community, namely us, so long to consider both gain and phase margins simultaneously? Maybe it didn't take so long. Maybe we're just getting to it now. But you pointed out Doyle and Sevenow's work from the 70s, right? I guess. And but anyhow, I'll just put that out there. It seems like it's taken us a while to get to this point. Any thoughts on that, or why that might be?
Yeah, accounting for gain and phase simultaneously, there's something called the vector margin, or if you could look in the Nyquist plot, it's the distance to the -1 point, which is, you can actually interpret that as just, it's not the disk I've given here, it's a slightly different disk. And the paper kind of talks about that connection. So that notion of a vector Nyquist margin, that you'll find that back in 40s and 50s as well. I think the real generalization is to the MIMO case, because in the SISO case, I gave an example where you can have really good gain phase margins, but poor disk margins. But it's really contrived. Like, I specifically constructed this example. And in the SISO case, generally it's pretty hard to get into this weird thing. And so I think the real benefit for me of these disk margins is the extension to the MIMO case, where there is a very natural and easy to compute multi-loop margin. And I think that theory was not as straightforward. You couldn't just draw like a SISO Nyquist plot and do kind of graphical analyses. You need to do something computational based. And so I think the tools just weren't around, and even up to the 70s and 80s to do exactly how it's done now.
Okay. That sounds reasonable. Thanks. I've got another question for you. Again, a little more philosophical. The viewer asks, are there any interesting examples or anecdotes about the application of disk margins in comparison to classical margins on vehicles? I guess we're talking about war stories or something like that.
Yeah.
Mind?
There was NASA had this generic transport vehicle model. It's a subscale commercial aircraft, and they had a flight test where it went unstable. Not anything went wrong, but the elevator started oscillating at a certain frequency. And the classical margins, I think I have an AIAA paper on this. The classical margins actually looked pretty good. But if you looked at the disk margins, they got very small at one kind of frequency, and it turned out to be the frequency that the elevator was oscillating at. And then if you took the disk margin perturbation, and I said you could then interpret that as a state space model, and you plugged it back into their high fidelity simulation, lo and behold, you could get their high fidelity nonlinear system to oscillate at the right frequency. So I think, generally when you're doing these robustness margin problems, most of the time nothing happens, because hopefully you've done everything well. But every once in a while, something bad happens, and this is just another tool in your toolkit, I think, to have. Like, there are cases where the classical margins don't actually get to the root of the problem.
Mm-hmm. That reminds me, your answer reminds me of one of your graphics here. Maybe you could cycle it. It's the one where you showed the diminishment in margins near the, was it 1 radian or 10 radians per second, flex mode. Yeah, that one. Yeah. So, you'd anticipate that, right? That seems to make sense at a gut level. But what this is also showing us is something at the lower frequency there, right? I just lost it.
Just under 1 radian per second.
Where
it's kind of,
you don't really,
the loop is
look at the Bodhi. Yeah, go ahead. Sorry.
Oh, sorry. Go ahead.
Well, I was just going to say, if you just looked at the Bodhi, you wouldn't think there was anything lurking there, right? But this is telling us another story, the disk margin, that there's some internal dynamics or something happening there that it sounds like in my head, I'm relating it to what you talked about with the ground transport model at Langley, the Aerostar, as I call it, 757. I mean, so this would tell you to go investigate here, right? Yeah.
If you look at the Bode diagram on the left, it's like just below 1 radian per second. The phase is starting to get close to 180. The gain is close to a crossover. So it's not anything obvious, and you certainly wouldn't see it in classical gain and phase margins, but it's, maybe there is something there. But yeah, it just gives a little more insight into what, where problems may occur.
Yeah, I think that's valuable. That's a useful technique. Let's see, a couple more. I think we have, a few more minutes here if you're up, if you're up to it.
Definitely.
You're on your closing chart. You talked about future work. Maybe you could take a minute or two and tell us, what do you see as new things coming in the I'll say the MATLAB robust control toolbox. What are some of the open research questions? If you could share that with us, maybe I think the audience might like to hear that.
I guess there's stuff that I've developed for kind of academic work, and there's stuff that I've developed inside the toolbox. I think the stuff that I've developed in the academic work that has maybe the most legs to be like useful tools as part of a toolbox are, things that have to do with gain scheduling or these kind of time varying analyses. So if I talk about the time varying case, let's take a launch vehicle as an example. You've got a high fidelity simulation. You run your case, and then you can linearize just kind of in one click of the button to get a time varying model along that trajectory. And then you could ask the question, like, how much uncertainty can I put along that trajectory before either it goes unstable or just the amount of like error at the final point of the trajectory is too big? And all those things are actually fairly easy in concept. Then there's kind of the numerical algorithm side, which wasn't quite your question, but getting something to work on kind of small academic examples like I'm showing here is different than having kind of an algorithm that will work kind of completely bulletproof. You can throw kind of any problem at it and it'll work. So part of it is just developing the numerical algorithms, and part of it is developing kind of the conceptual tools to do these time varying analyses.
Okay. Hey, one last question, and we'll wrap up here. In the MATLAB robust toolbox, is the representations there essentially what you described here? One of the viewers noticed a little deviation in one of the formulations, but is it by and large the description you've given us today?
This code, the command line code, I think I literally just ran in 2020A. If you ran it earlier version, R2019B, this might be slightly different. Like, I think we added the perturbation not in the first release that disk margin came out. Okay. So it's possible, depending on the release running, the output syntax maybe doesn't look exactly like what I've done here, because this is 2020A. And then the Simulink, there's some kind of Simulink infrastructure. Again, that depends exactly on the release that you're using.
Okay, that makes sense. Perfect. Well, Peter, I think we've addressed all the questions that have come in. If something, typically questions come in a little bit late. If I get a couple more questions, I'll pass them on to you, and perhaps you can respond to them. So I think we've run out of time. And by the way, thanks for agreeing to follow up with any late arriving questions.
Definitely.
So let me start the process of wrapping it up here. I just wanted to communicate to the audience that we are actively soliciting feedback, not only on this particular webcast, but also on the overall series of NESC GNC webcasts. Shortly, an email will be sent out to all the audience participants. It'll provide a link to it's a brief and simple online survey form. We'd like to collect your feedback that way, so please take a few minutes to fill that out. We'll also be sending out another email to the entire NASA GNC community practice, providing a link where today's recorded webcast can be viewed online in the near future on the NESC Academy site. We have several of those up there. The Webcast Planning Committee is always looking for ideas for future webcasts. So, things that would be of general interest to the GNC community practice. If you have ideas for other relevant GNC webcast topics, please contact me. If you have a topic you'd like to bring forward as a webcast event, by all means, get in touch with me. We'll talk about it. So I just want to thank you for participating with us today. I hope you can join us again at our next GNC webcast event. And thanks once more to Peter for taking the time to put this interesting package together and brief it to us. I think it was well received. We had a large turnout today. But this completes today's NESC GNC webcast. So goodbye for now.